This.
Hi. Hello. Deep.
Yes.
Hello.
हाँ नितेश
सुनाई दे रहा है क्या?
हाँ
घर पहुंच गए?
हाँ
मैं अभी ऑफिस में हूँ, ऑफिस से अटेंड कर ले रहा हूँ। घर जाने का टाइम नहीं हुआ, लेट हो गया मतलब
अरे कहाँ है आपका ऑफिस कौन से में काम करते हो?
क्लियर ट्रिप में, जे जयदेवा सिग्नल के पास, जेपी नगर में।
अरे बाबा वो तो बहुत दूर है।
और सिल्क बोर्ड क्रॉस करना है ना।
बाबा
हाँ, यहीं से अटेंड करना पड़ेगा आज।
नहीं तो मोबाइल पे लगाइए, चलते बनिए और क्या।
कोई दिक्कत नहीं।
10:30 में जैम रहता है क्या?
कहाँ पे?
10:30 में जैम रहता है सिलपुर।
सिल्क बोर्ड में हमेशा रहता है।
अच्छा, सिलपुर का कोई माँ बाप नहीं है।
Okay, so everyone is here?
Hi.
No? Hi.
No. Me and Subhadeep
Okay.
are here.
Okay, Vasant is the only one person not here. Let me just bring last time. Can you see the editor?
Yes.
Okay. Okay. So as I told, I wanted to discuss assignment first, but let's start with the dynamic programming. Then we'll do the discussion about the assignment later. Okay, let's start with this. Agar time milta hai, so we'll do the assignment also. By the way, Subhadeep, did you do the assignment or anyone? Assignment किया किसी ने भी?
नहीं, मैं कोड तो नहीं लिखा मैं, बट
एक्चुअली नाम ही असाइनमेंट का नाम ही खराब है। कुछ भी बोलो तो नहीं करते, कुछ और बोल के दे दो, सब कर लेगा कि इंटरव्यू क्वेश्चन है, प्रिपेयर कर लो, एग्जाम में आने वाला है, सब कर लेंगे।
कल इंटरव्यू में पूछने वाला है वो, तो अभी बैठता हूँ मैं इस क्लास वगैरह छोड़ के।
ठीक है, he's not replying, so let's start. Okay. So I've heard people saying the dynamic programming समझ नहीं आता है. So thing is, even I was like little bit not sure what exactly dynamic programming is, but okay, Vasant might be joining. So somehow I tried to relate all the problems of dynamic programming with recursion. Now recursion is another problem which people are not so much confident about. But if you understand recursion a little bit, then solving a dynamic programming becomes very easy. Obviously, you have to understand the recursion. So that's why, as per the demand of Athar, I have tried to find out something to what can I teach in recursion. Actually, there's nothing special to teach in recursion, but still, I'll try to do something about how to understand and how to figure out whether recursion will work or not. Something like that. We'll try to discuss a little bit, and then we'll go ahead with the dynamic programming. So, as I have written, so any method, we will call it a recursive method if it is calling itself. If it is calling itself, we'll just call it a recursive method. So example here is, this is a method. This is calling itself once again internally. It might call it twice, thrice, or n number of times. It doesn't matter. But if it calls even single point of time, it is a recursive method. And normally we can easily relate any given solution or any given problem, it's easy for us to determine what is going to be the recursive method for that. So one example is finding factorial. We want to find the factorial of a value n, and if we know the factorial of n minus 1, we can easily calculate the factorial of n by just multiplying n with the factorial of n minus 1. So this kind of feeling only will let you know, yeah, can we do recursive method, or what would be the iterative way? Draw a loop, write a loop from 1 to n, and then keep on multiplying 1 by 1. So that is going to be another way of finding factorial. But if we think other way around, like what is the factorial of n? So the value is factorial of n is n into the factorial of n minus 1. So if we can think this way, then only we will be able to write. There is no special trick to think. This is just about how do you realize this problem, then only you can. Okay, so this is a very simple example of a recursion. That's why we could easily say that we can solve this. Let's take another example of a recursion. If you remember, I gave this question in some of the class, reverse a linked list. So reverse a linked list, we can do it in a recursive way as well. So if you remember, what is the question, reverse a linked list. All of us did the iterative solution for this. Just went to each node and then reversed that node and then went ahead. Given a linked list, we had to reverse this. And how did we do this? I think we did this using iteration.
3 pointers.
Yes.
Yeah.
3 pointers.
Yes, 3 pointers. Now, this problem can be done if using a recursion as well. So if you try to think, how will the recursion look like? So we start from the head node, that is 1, which is right now at 1. So if you just break it into 2, like mostly recursion is either 2 sub recursion or 1 small base condition and then rest of the recursion, or it can be any small n number of sub problem and then collectively use all those sub problem to generate the solution of the main problem, the bigger problem. This question is a example of a recursion with only 1 sub problem. So what that sub problem means is, if I just start, so I have this head, if I just solve my question for head.next, so if I just assume that this, instead of starting from head, if I call this recursively for head.next, and if I get the output of that, what will the output of this be? So suppose head is equal to this 1, and instead of solving for head, so we had to solve for head. The main question solve this, or whatever solve is, or whatever, like reverse a linked list, this method for call this method for head. So instead of thinking about head, just think, what if I call the same method recursively, obviously, for the next, instead of 1, call it on 2, what will happen? So we're thinking, this is a new question. What will happen? This will give an output, and output will be 9. Output will be this. So, when we wanted to find this solve head, we just did a solve for head.next. Can we use this? Can we use the output of this solve.next to get the final solution? This is the final solution we want. And we have solved only for the one part of the problem, which is from 2 to 9. We wanted from 1 to 9, but we just solved from 2 to 9. Can we just use the solution and get the solution for the overall solve head? So yes, what we can do is, so the solution of this is returning head is something. So I'm assuming that this solve method was returning head of the linked list, of of the output linked list, as well as suppose it was written tail also. Okay, this is not a code from Java and C. This is pseudo code. Suppose this method solve head is returning my new head as well as new tail, something like this. Okay. Now, assuming these two values we have, can we just use these two to solve for our head? So I'm just writing this once again. Our method, which is solve, this we start from head, and I am calling this recursively for head dot next, and I'm assuming the return type this is node comma node. Suppose this is some way similar type. It is returning two nodes, array of two nodes. Okay, or in your Java language, it returns two nodes. First is the head of the new, and second is the last, the tail. So this will return me two things. One is the new head and one is new tail. Suppose this does this. I'm assuming कि हमारा method जो है solve for head, it returns me correct new head and correct new tail. Now once I call this, can I just simply use my head and these three, so these two and this head, can I use these to just return the correct thing? At that I want to return two things. Can we use this now? So the final output will be new head will be this only will be written, but tail will change. So new tail dot next is equal to head. See this? So we solved for rest part of the linked list and used the output of that. So the tail was 2. So we have used tail dot next is equal to head, tail dot next is equal to 1, and we just returned this head. Okay, now I haven't written base condition. There's something called base condition. Whenever we write a recursion, we should always be sure in our mind what is the base condition going to be. Mostly the base conditions are like when n is equal to 0 or node equal to null or last node, something like that. That will always have to be there. There's some terminating condition, base condition has to be there. Otherwise, do not write a base condition, your recursion will go forever and then you'll end up with stack level too deep kind of error, or memory consume, complete memory consume, that kind of error you might end up, because it will just keep on calling recursively for infinity and then store all the recursion level in some stack, and then the error would be stack level too deep, something like that. So always have a base condition, and I would prefer you people to think about the base condition initially. If base condition equal is met, if base condition, then return either you return out of the or return something or something. So this is the base condition. Whenever we write a recursion, we should always be thinking about what is the base condition, where will I stop this recursion. And once we have written for the base condition, we can then write our generic recursion, which is like I should be aware of the sub problem which I'm going to break. In few cases, it will be half sub problem. In few cases, it will be only one half sub problem. In few cases, it will be like only one of the. In this case, it was like complete list is a sub problem except one node. So understand? Let me draw something once. So if this is a big problem, then sometime this will break into two sub problem, like either this and this. This is one kind of recursion where you break your problem into two sub problem. Can someone give me example of this where we have a problem and we can break that into two sub problems?
Merge sort.
Merge sort. Nice. So when we want to merge No, that is
divide and conquer. So we
yeah,
divide.
that is not, yeah.
Yeah.
You first divide, and that is slightly different from your recursion. But let me think of a question, which is though. Okay, before I give example all of this, let's come to one more example. Is your main problem is related to only one half of the problem. ये तो example सबको पता होगा. This is the main
binary search.
Yes, binary search. Okay. Then there is another kind of recursion in which your problem is broken into two sub problem, but that is not half of it, but that is like, sorry. Which was the current thing we just did. This is also your one kind of recursion where your problem is broken into only one bigger half, which is like just we have saved for this much, and then rest of the recursion is called in this. This is example of this. Even factorial is similar. We have called recursively on the smaller half, but that smaller is just one smaller than the bigger main problem. So this is one kind of another kind of recursion. Okay. Now, so we have, this is a binary search. This is a reversal linked list or factorial, and just everything. So we want a question where we break our main question into two sub problems, equal sub problems. That will be
Equals binary search, right?
Binary search. No, binary search is only one sub problem.
Oh, yeah, we go to only one side.
Yes. So calculate the height of a tree. Calculate the height of a tree. So calculating the height is calculate the left height and right height. So this is height.
Right.
So height of tree is this. This is binary search. And this is factorial. And then there can be one extreme is like break your problem into multiple, like more than two subproblems or three subproblems. But this is what recursion is. Your main subproblem is broken into multiple subproblems. It can be only one subproblem, it can be two subproblems, it can be n subproblem. This is what recursion is. And all of these will have a base condition. And how do we reach a base condition? Whenever we're dividing the problem, it ends up at the end, there will be a case when your problem will be so small that you don't have to call recursive. You can simply return that without even calling it, you can simply return the value. In this case, in this case, suppose we reach this endpoint. In this case, so we keep on reducing. At the end, you reach only this part, and you know a factorial of 1 is 1. Hence, I will return 1. Instead of calling recursively on 1 half comma half, we'll or 1 comma 0, will not call recursive. We'll just return. So this is called terminating condition. In every subproblem, we'll have a terminating condition. It's not just one of them. All of them will have a terminating condition somewhere. And that is what is very important. How will you think that terminating condition or the base condition? Okay? So with this example, I don't have much thing left here. So one thing is, mostly your sub problem will return something which will be used in our main problem. That is one thing you also have to take care. Every time you call a sub problem, you have to return something from there. If it is, returning. So again, one more thing is you decide the return of the recursion first. The first thing, one more thing you have to do before you start writing recursion is, what is the return going to be? Return of the method. If you decide this, then writing your recursion would be. So you have to decide kya return kya karna. What do you want? If you decide that, then you can assume that the noise coming. Okay, so I missed this. So what I'm saying is, if you decide the return, what is my recursion going to return? If you decide that is one thing you have to do for sure, and that will make your life simpler. Then second thing, you have to assume one thing. If you're able to assume very simply, my sub problem is going to return the correct thing. If you assume that, once you first you assume what is going to return, and then you assume my sub problem, which I'll just write. So while writing a recursion, let's clean this screen first. So while writing a recursion, first steps would be decide the return type. What are you going to return by recursion? And then second is identifying. Actually, it might be wrong, but I'm just trying to write what I think. Identifying the sub problem. What that sub problem can be. Third would be assuming that recursive method which you're writing, which you're implementing works perfectly for the sub problem you just thought. Sub problem. So if you assume this, then you can use the output, which you use the return or output of the sub problem you just solved above. So if I try to write code for this again, so take the case of factorial. So we want to implement this. So first step is decide the return type. So we know we want to return is factorial, which is going to be integer. The first decision should be this. We have missed here the base condition also has to be thought, not solid but earlier only. Now factorial of n we want to write. Second thing is identifying sub problem. Now people can think, what can be sub problem be? Can I break into two half? Can I do it a factorial of n equal to factorial of n by 2 and can I use n by 2 and n by 2 and solve it? No, we cannot. If you think we can't do it, we can't break into two sub problem or third sub problem. We only way to solve this is if you can get f of n minus 1, factorial of f of n minus 1, then only I can get the factorial of n. So this part is there is no special theory for this, how to identify sub problem, but that you'll have to think. Now assuming that the recursive method works, so I'll assume my recursive method works and the sub problem I have identified is n minus 1. This is a sub problem, n to n minus 1. Assuming this will work, correct output. This is correct, correct output. We have to assume this for n minus 1 is equal to this. Now, since we have assumed this, we can use this value and return n into this. So since this is correct, this will also be correct. So that's the another part. Using the return of the output of the sub problem which you just calculated and assume that this is going to work, hence this will also work for sure. Now comes the last base condition. When do I stop? And how do what happens if f of n minus 1 is I'm just decreasing 1 by 1. There will be a time when this will become 0 and then become minus 1. So you have to stop somewhere. Where do I stop? One is where I can where I know the value. So we will obviously call only for we are assuming that we are calling for positive number. So by decreasing 1 1 1, we will reach a point where it will be equal to 0, and we know that factorial of 0 we know without I don't have to calculate myself by using this. We also know the factorial of 1 also, and sometimes it's not necessary that you only have to find the last one. You can, if you know the factorial of 2, you can take this also. You can take this also as your base condition. So if n equal to 0, then return something, return 1. If or return 0, factorial of 0, suppose no, factorial of 0 1. So and if this is equal to 1, then also return 1. So you can write as many base condition as you want. It's just that if you up to you how many base condition. If you write base condition for n number, then it doesn't make sense to write this method at all. So you can write as many base condition you want. I know for 3 also, so I can write for 3 also. So it's like implementing this complete method manually only. But I don't require this 2, and I don't even require this 1 also, because anyways, if I get it for 1, I call it for minus 1 0, and then I return this 1 here only. So there are two return. One return is for the base condition and other return is for the normal condition. So this is going to be case everywhere mostly. One return with the base case and one return with the your generic recursive method. This is going to be everywhere, most of the cases. So yeah, that's about the recursion. Now, if you have any question, ask. Otherwise, I'm going to move to our actual thing, dynamic programming (DP).
Praveen,
Yes.
can you talk about backtracking a little bit?
Backtracking. Okay. Why do you think that is related to this?
It looks like recursion only, right? I mean, we call the same method, and while coming back, we do some operations.
Yes. So backtracking is a case where we try to solve using recursion, or not necessarily recursion. We try to solve, and then we get the solution. If that doesn't work, then we revert back that sub, and then we call with the some other case. Let me think of a question. So there are multiple possible ways to solve this, and we try each one of them one by one, and whichever works, go ahead. Otherwise, we come back. So let's take this example of n by n queen. I might not. So there's a question. Place n queen in a chessboard. Anyone has heard this question? In a n by n chessboard, n cross n chessboard. Just give me a minute. Okay, anyone has heard this question?
No.
Okay.
I have heard, but don't remember this.
No problem. So we have a n by n or let's talk 9 by 9 or 8 by 8, whatever, the normal chessboard. 9 by 9, 8 by 8, sorry, 8 by 8 chessboard, and we want to place 8. Is it 8 by 8? Yes. We want to place 7 or 8 queens, and so that no queen intersect each other. In the sense, none of them have same row and same column. So can we do it? I do not remember if there's 7 queen or 8 queen. Can we do it for all 8 of them?
I think 8 queen. It's 8 queen problem.
Yeah, 8 queen problem. So we have to place all the 8 queens. So that will be easy, no? That will be easy. 8 queen problem in an 8 by 8. So we just store everything on 0, 0, 0.
M queen problem.
1, 1. What?
M queen's problem.
Yeah. So what was the exact problem? Let me search the problem only. Or do you have any other question for backtracking?
Permutation of a string.
Yes, that is also there. Just the question is, we have this the n queen problem is the problem of placing n chess queens on a n by n chessboard so that no two queens attack each other. For example, okay. Okay, yeah. So n queen problem has one more thing. The question is that thing only. Yes, one thing I was missing was they can attack each other in the diagonally as well. Okay, so we cannot place. Let me not draw. So the question is same. N queen question where we have a n by n chessboard, and then you have to place all the n queens and they so that they cannot attack each other. And what do you mean by attack? All queen can travel complete straight or horizontal or diagonally. So no one should be in the row of each other. No one should be in the column of each other, and no one should be in the diagonal of each other. So that is the third condition I was missing. So this is a sample of a 4x4 n-queen problem. Can you see this?
Yes.
Yeah. Okay. Now, if you see this, all four have been placed in such a way that they are not able to attack each other. Okay. So what they try to do, what solution is, this is one of the backtrack question. We solve for, we start with our environment chessboard. We start with the first queen. We place it wherever we want, the first place. That's any. We don't know what is going to be the best solution. So we try each and every possible solution. This is one of the kind of looks like a brute force approach only. But sometimes that brute force approach might not be very efficient. But this is what's going to work only. So we take the first queen and we place it at 0,0. Okay. Now once we place at 0,0, our problem is reduced to a small problem, which is just place your n-1 queen now. But this time you cannot place it in 0th row and 0th column. So that is with condition, and then you can place your next. You keep on doing it until you reach a situation where you have no option left. So suppose I was doing it the most simplest way, which was I started from 0,0. There was no queen initially. Everything was so the first queen I placed here. Okay. Second I placed here. Done. The third I placed here. This was done. Fourth, when I place here, I find it a little bit problematic. I can't place it here. Hence, I'll have to go back. I can't place one here, so I'll find a better position for one. So now this can't go here. So can it go somewhere else? We already had discarded this. We already had discarded this. So and we had placed here, but now we can't place here as well. So let's try to place one here. Now we're done. We come back again and we find a proper place for the last one, and then we again start from beginning and we try to find the correct position of this, which might again we don't find a good solution, so we have to backtrack to the next even upper level. So this is in terms of backtracking. Like we have to if you talk in terms of code, so just a minute. I'm copying it from somewhere else. Okay. So what if you see this part of the code? Yeah. So what they are doing is, again, for all the queen, it's taking queen one by one for 0 to n. You're taking all the queen and checking if queen can be placed at so just a second. We are starting with the column and basically. In this board, can I place my queen at ith position? If it is it safe? Otherwise, if it is safe, then place it at that position. Otherwise, solve for column +1.
If ही condition है वो तो पूरा. If it is safe, then only.
Yeah, this is implemented separately. This safety check will implement this separately. But so we are solving this in we have the board and we have the column if all them are placed, and we are returning it when all of them has been placed. When this we coming out of this if all of them has been placed. Just a minute. Base condition is here key if column is more than equal to n. So this is recursively calling. Where is this calling recursively? Solve of this thing is getting called recursively. Here it is. Okay. So this here we are maintaining how many queens has been placed. So the moment all the queens has been placed, we come out of this is the base condition. So this is a recursive method along with the backtracking. So this condition is checking if all the queen has been placed, then just come out of it and we are done. And this is the board we are placing. At then our board will contain all the queens. And this is what we're doing for, this involves a recursion as well as iteration as well. So this is calling it recursively, solve nquutil is calling recursively, but inside this iteration. Now, if you see clear, like if you try to see, we are calling recursion how many times? What I taught was earlier. What I taught earlier is a recursion is a method. A recursion method is a method where we call same method itself. That is a recursion. If you see this same thing here, this is calling recursively and not just one time or two times. It is calling it n times inside. It is calling this solve solve this the bottom method n times for n equal to I equal to 0 से लेकर I equal to n तक, doing it multiple times. Doing for all of them, for first queen, for second queen, and for last queen, it is doing for all of them. So now if you go deeper, so we just take the first queen and we try to place it at ith that position. If it is safe, then we place. Otherwise, where do we backtrack? So if it is safe, then we place it, and then we increment our number of queens placed. So we have incremented, and we check if it is. We call recursively for the next part. This is a recursion. So we have called for the first queen. Now we started from 0th queen, and that 0th queen placed it properly. I'll go at ith position, and then I'll call for first queen. This first queen will try to call for 2 and whatever recursively, and then it will return true. If it returns true, then it means I can place my 0th queen at the correct place. So that is what it means. Simple, or it is so many things are hidden in a single line. So I'll repeat. For ith queen, I'm checking. Can I place my ith queen at? Column? So we are doing this for. Sorry. Can I place my queen, column's queen, not ith queen, column's queen at ith position? This is safe in the board. Can I place my queen at I comma column? I am incrementing my column every time I call recursively. So this is checking. Can I place the queen? Which queen? Just a second. So consider this column and try placing this queen in all the rows one by one. So as I said, key. This column is the queen I want to place. This column is acting like that. So I want to place 0th queen. I'll call this method only. So when we call, how do we start this method? How do we trigger? We trigger this method like this. We start with 0. So I want to place 0th queen, and then I have to find this is what we call this recursive method with initially. Obviously, this board will be something. So, and where do we come out? If I can place queen 0, I'll be incrementing this column. I'll increment this 0 here. This is where I increment. So, again coming. So we start with 0. I want to place queen 0, and that is returning true only if my queen 2 has been placed. I mean, not to queen 1 has been placed. Queen 0 and then queen 1 has been placed. It means I can place my queen 0 also wherever I placed. So there are two things I'm checking. Can I keep this queen 0? Can I keep this queen 0 at ith index I? So we are changing I. Can I put it 0? Can I put it at 0, 1, 2, 3? Taking for all. And for all of them, can I put my next queen at this place at next row? I'll try to draw a diagram now a little bit.
Yeah, क्योंकि कुछ समझ में नहीं आ रहा था मुझे तो.
Yes.
तो ऊपर से जा रहा है पूरा.
Yeah. Let me draw something for you. So
ये DP और backtracking एक ही है क्या?
नहीं अलग है. Okay, so if you see this method which I've written here, solve for on this board and solve for this.
Can you copy is safe as well? Means how they are doing it.
I'll copy, but safe is what we know. Safe, I'll define that. Otherwise, you'll be more confused. Safety means ki I'll tell what is safety. Let it come there. So safety is if already there are some queens already placed. Suppose I have already placed one queen here. Suppose I have already placed one queen here, and suppose there are some queen here. Now putting one more queen at some other place and checking safety is just making sure that this queen not in the path of anyone else. That is what it means, safety. So there should not be anyone already. There should not be anything in this column and in this row and in this diagonal. That's what safety means. So every time we call this safety, we just check these four things. There should be no one in this column, row, and diagonal. That's it. I'll copy that method also. Let me copy them. So this is a board which already contains some queen, and then this is the new queen I want to place, and we want to check whether this is safe or not. So what we do, we just check in this board, is there anything already present in that row? So row of I and board of I and J. So this is both the things we have checked. Is there anything already? This is for checking for diagonal left, and this is for another diagonal. So this is for one. I'm going from I equal to 0 to I less than column, and I'm checking for all the columns. Is there anything in that column? And this is for checking in the diagonal if anything is put in the diagonal. And this is also for, where is one more check? There should be one more check for one column we have done. What is the check for the row? So we have something already there. We have something here. We have something here. Suppose now I want to place this one more thing in this row. So okay, so they're not checking. One more thing is just row, because we know there's nothing in this row, and we're just trying to find the correct column. This method is not checking for key. Is it colliding with any? I mean, is there a problem in keeping this row? Because I'm calling this method only when I'm sure there's nothing in this column, in this row. Sorry, this checking only three things. One, can I? So now I want to place somewhere in this row. Okay, that's the problem. I want to place in somewhere in this row. Where shall I place? So I try everywhere, and what I check is safe. And what is that if safe? Can I place here? No, because there's something in this column already there. Can I place here? No, because there's something in this column already here. Can I place here? There's nothing in this column, but there is something in this diagonal, so I can't place it. Can I place here? No, because there's something in this column. Can I place here? No, again, nothing in column, but there's something in this diagonal. So can I place here? Again, no, because this is nothing. Although there is nothing in this column, but there's something in this diagonal. Can I place it here? There's nothing in this column. There's nothing in the diagonal. There's nothing in the left this diagonal. But we're not checking only. Is there anything in the row? Why? Because we already know we want to place here. We can write a condition that also, but the way we have used the safe method will tell you we don't have to check. Okay, so this is what if safe is doing. This is checking in the complete column. This is for one diagonal, and this is another diagonal. Vasant, do you want to go deeper in this method?
No, I got it, but they are not checking
row
vertical wise, right? Yeah, it's vertical wise.
So as I said, while placing only, you can implement that, but that will be of no use, because the way we are using is where to place the point of this is safe is, I know I have to place in this row. Where exactly is I want to find? That's why let's go and let's check how it is getting used.
Okay.
आई थिंक, और ये कॉलम तक ही जा रहा है, जहाँ पे कॉलम, जो कॉलम का नंबर है तब इंडेक्स है वहां तक ही. सो
हाँ,
जो
हाँ. I'll tell you. So while now how this backtracking thing is working is, we want to place queen in each row for sure. Since we have to place 8 queen, ये तो पक्का है कि हर row में एक जाएगा. There is no way that any row won't have a queen. So we know for sure. So and every time we start, so what we're doing, we're just looping through all the row and finding the correct position of queen in that row. So इस row में initially तो यहाँ पे कुछ नहीं था, so it was easy for us to place queen here. We just placed our queen. So initially we just placed our queen here. Now we know कि इस row में भी now to second row इसमें भी place करना ही करना for sure. तो which will be the easier first, the greedy approach will be एक करके जाते हैं and then we find this is only the good place for it. Just kept it here simply. Now again we just moved slowly and we one more step and we know कि इसमें यहाँ पे तो रखना ही रखना है. So I'm coming to the point where we are just keeping one by one, and this part here, this is doing for all of them. For I equal to 0, I'm finding the correct position by this method. I'm finding for each queen, I started with 0th queen, what is going to be the correct position. So it just places it at the column ith row and column position. What is that? Sorry, again I'm making the opposite. Sorry. So column is, it is doing reverse. I'm talking reverse. It is doing reverse. Column is, I want to place it in this. Let me delete. So first I start from this column, 0th column. I know कि इसमें इसी column में रखना है. Now in this column, where should I put? I should push it here. This is going this direction. I was going other direction. So again to start, this loop, this most external loop for I equal to 0 to n is for all the queens. ये समझ में आने के बाद we have to do for all the queen, and for each queen I try all the possibility. Now
कॉलम कांस्टेंट है, रो वाइज जा रहे हैं.
Yeah. So this is for all the queen. I try to place my queen at ith row and column position. So column is first I place in this column 0, and I place at this position 0 0, and then I board of I column, this is what I'm placing, and then I call recursively with second column because I want to place this in second column only. So this, or first column, not from 0 after comes that one. So I want to solve for rest of the sub problem, but after in 1th column I want to place my next queen in this column only, somewhere in this column. So where is this happening? Like, where are we checking? So we are checking this is safe. If it is safe, then only go ahead. Otherwise, change the I. Don't place it here. It will call for. Let's try to write this. So we started with the board B, and we started with 0. This is we'll start with. Is it visible? But it's too small. Okay.
It's fine.
Now it's fine. Okay. So we will when we will stop when we have placed all of them, which means when this 0 becomes n, and then we start with for I equal to 0 to n. For all of them, we first check if board is, if it is safe to keep it in 0, 0. Yes, it is safe. So we go ahead and make this value our board of 0, 0, we have marked it as 1. Just like I have placed one queen here, and after that I'll call for this recursively S on the board B with 1 incrementing. I'm incrementing this, and then I'm checking if this is placed properly, then I can place it here. So I'm just checking, can I place one here, this first queen here? If I can place this here, then I'm sure then I can place my previous queen in that place only. Otherwise, if I'm not able to place this, if this is not allowed, then I have to find a, if I'm not able to, if this is not safe, then what do we do? So this was safe, hence we placed at S of at 0, 0. If it was not safe, then we would have moved this somewhere else.
We are moving to next row. Right.
What?
We are going to next row, and then we are doing...
Yes. So in this column only, we cannot place it here because our recursive call, this recursive call, where is this was not safe. If it is safe, then we could simply, sorry, this was safe to place it there, but this recursive call said that you cannot place me at this, in this column. Sorry, I'm confused between columns and rows. So this was not returning true. Hence, I have to change the position of this thing only. I have to backtrack. I have to find some other position for this. So I cannot place it here. Let me delete this. I cannot place it here. Hence, I have to change the position of this zeroth cone only somewhere else. I have to try with this. Can I now with this? I'll have to try for completely backwards. I have to try for all of them. So I started with this column. I will not discuss the code right now. Let's discuss on the this drawing only. Then we'll come back to this code. I'm not seeing the code right now. So I placed my first queen here. Now I know that this is it might be a good position for my first queen. Now second position, the second queen will go in somewhere here only. That's what I want to. I'm not going that way from the code. I'm just thinking myself. So second queen will for sure go in somewhere here. Okay. Now I'll just check what is that. I'll just assume it can be placed here. And once I have placed it here, I'll do further this, and there will be a point. There will be a point when I won't be able to place my next queen at any of this. If I keep it at any other place, people noise. Yeah. Okay, so my solution of this, I'm backtracking. Where's the part? This is the backtracking part. Is safe to place, then go ahead and call recursively for the next. And if the recursively returns true, then you can go ahead and place. Done. Otherwise, try me at some other position. So for every queen, I'm trying all the positions. So I'm trying this, I'm trying for this, and then recursively for I call for this. Okay. So every time I solve for column with queen, I just try for all the position. I just recursion here is I'm trying for all the queens. So I'm trying for 0th queen, and then for 0th queen, I have to try for all the. Again, people do not make noise if you. So what I'm doing is for every queen I'm trying all the possible columns. For every queen I'm trying for all the possible columns, which and so how do I try for each possible column? I keep it at that column. Okay, I keep it at that column. I call recursively for the next queen, and the next queen for sure will go in this row only, and then I tried if it can be placed anywhere. If it can be placed anywhere, then I can assume that it can be placed at the position of which I tried. Otherwise, if I'm not able to place second queen, then my previous queen will have to go somewhere else. So this trial, this loop, again, I'm trying to repeat things. So this loop is to try all the position for the column queen. This loop is here, is to try for all the column. Okay. The first, suppose I reached here. Suppose I reached here. Suppose I placed my all the queen from here to here till now. First queen, second queen, third queen. We have placed properly. Now I want to try for fourth queen. This fourth queen, again, I'll try for all these index, all these column. Can I place here, here, here? Wherever I can place, I'll place it there. And if I find some position, good. Otherwise, if I don't find any position, I'll have to revert back. I'll have to. So if I find some position, good. I'm trying for this. I'm trying for this. I'm trying for this, and I'm trying for all of them, recursively for all of them. So what is the backtracking here? If I'm not able to get any proper position for this, what happens? So this loop is for trying all the position, and for I check for this, can I put it here? Not safe. Suppose this is safe. I put it, this was safe. Now I put it here. I go back and try for the next one. And then again I try for all the position. This. So this is a very if I'm able to find a position for this, good. Otherwise, I have to make it. I have to remove this from here and then try for next. Okay. So what I was missing was how I was trying. How I was trying for all the columns. So again, I'll repeat from the beginning. So we have to call this method solve for util for all the queens. This method has to be called for all the queens. This is the main thing. So we start with queen 0 and then we call this for all the queens. Now, what do we do for all the queens? We try for all the columns. So we did for 0th queen and we tried for all the columns. This column, this column, this column, this column, this column. So while trying this column, while trying for all the column, I have to call recursively for the next queen. If that recursion succeeds, then it's okay. If that recursion fails, then only we change this and then again call recursively. So this is the part where backtracking is happening. What I'm doing is we are trying for ith queen. We're trying for ith queen, and for us to try, what do you mean by trying ith queen? I'm trying to place ith queen in the ith row. Okay, let's call I equal to 4. I'm trying for fourth queen. That where should the fourth queen go? And what I'm trying, I have to try for each column. Which column should it go? I tried for first column. I keep it here, and I call recursively for the fifth queen. If that fifth queen passes in, then it's good. I can place it here. Otherwise, I'll backtrack, which means I'll remove it from here, and then I try for this. So this loop for I equal to 0 to n is trying all the columns. It's trying all the columns. So it tries here, it tries here, it tries here. And what does it mean by trying? It calls recursively, and what it does, it places everything. It places for this whole left. It places everyone, and while placing everywhere, I might reach a situation where this is not going to work. Let's go back, come here again, and then try this. So this, what I draw right now, I'll try to do once again. So I'm trying for queen number 4. I have placed my queen number 1, 0, queen number 1, queen number 2, and queen number 3. I'm trying for queen number 4. So for us, and what is the trying means? We have to try for all the, that's what. Simple thing means I have to try for all the columns where all I can go. So while trying, I call recursively for fifth. I call it 0th index, 0th column, and I want to place my fifth queen. I can place, I can solve for. So suppose that solution was there. I can place my fifth. Otherwise, move it from here and then try for 4 when 4th was here. Remove it and then try for 4 when 4th was here. So this is what is happening here. And now coming to the code. So we have to call this method. I told we have to call this method for all the queen. Now for all the queen means just increment 1 by 1. And if the moment we have solved for 7th queen or 8th queen, we can return completely true. Yes, we can come out of the recursion. Now what I mean, so let's try for column 0. Column 0 is means zeroth queen. I try for zeroth queen and try for each column, column 0, column 1, and we are trying for each column. And if I find this for each while going from 0 to n, if I find yes, I can place my current queen at this column. Sorry, if I at this I, not whatever. If I current, this code is reverse. What I'm talking is slightly opposite, so I won't be going through the code. What I'm trying to say is this loop is to go for all the options. But what I mean by all the options is I will try for all the columns 0 to n, and I'll try to place my that ith row queen into all the position columns, all the possible columns. So this is for all the possible columns, and at every column I call recursively for the next queen. If that queen can be placed somewhere, then I assume this is correct. Otherwise, I backtrack. I change. This is the backtracking part. We have changed it. This loop part, and I try for next. I try for next queen. If it is placed there, good. Otherwise, I make it somewhere where I'm making it null. This is the part where backtracking happens. This is the part. So initially I made it is if it is safe, then place. Otherwise, just make that thing also 0. Don't place it there. Try for the next column. Okay. If you haven't understood yet, I'll go and try to write a code the way I told. This is the reverse of that. Or let's try to understand this only. See how they are doing.
प्रवीण,
Yes.
मेरा तो कुछ अंदर जा नहीं रहा है तो ऊपर
No, that's right, because the code is different. What I was saying was different, so I will try with what code is written. Okay, I'll try with what code is written now, so you'll understand this time. Yeah. So I'm trying for each queen, and what does that mean? Trying for each queen is I have to place every queen in somewhere in the this column only. So first queen will go into this column for sure. First queen has to go into this column, and second queen has to go in this column. This is decided. I have to place my first queen in this column somewhere. I have to place my second queen in this column somewhere. That is pre-decided. That is, we cannot. Okay, this thing is already decided. So that's why if you see this method, solve nq in the nqueen utility method, whatever method, for zeroth queen, or we start with 0, or we call it first queen. That solution will depend if we can solve for second queen, if we, or this queen. So if I can place 2 somewhere, I can place my 2. I can try for all the ones. So this is now coming to the code. I'm trying for first queen. Where can that be placed? So I have to try for all the rows. This is what all the rows means. For I equal to 0 to n, I'll place this current queen at all the positions. Which, and in this case, the current queen is first queen. I'm trying here. I have to try here. I have to try for all the positions. So this trying for all the position means just try to place your second queen in the proper position. If you just place the second queen, if it is safe to put your second queen, then put it. Then you can mark myself as, so this condition. If it is safe to place your current queen at this position, and also this is 2 things here. So there are 2 things we are checking. Can I keep the current? So I'm trying for all the rows. I'm trying for the 0 equal to n. I'm trying for all the rows. And can I keep that queen here? Yes, I can place it here because there's nothing already there. I have to try for all of the rows. So this is for trying all the rows. And can I keep the current queen in this row? Yes, I can put here. Why I can put here? Because there is no other element already. So this is safe to keep it. There's nothing in this diagonal. There's nothing in this diagonal. There's nothing in this row. There's nothing in this row. So it is safe to put here. So if it is safe to put it at ith row, okay, if it is safe to put it ith row, and this case ith is 0 only, and it is also possible to place your next queen somewhere. Next queen, which will for sure go in this column only, and there's a way to put it somewhere then I can go here for sure. Then I can go here. This is what means. Again, we are giving preference. We are giving preference to the first queen, that you go at the best position, whatever you find possible. Then second will find among the rest of the positions. So this second will find next queen will find a position in an already filled board, in a partially filled board. In a partially filled board, it will try to fit somewhere. If it can fit, okay. If it can fit, so what does that fitting means? Well, that fitting means that I should not be getting placed in a wrong position, and also my next queen also can find a position. So this is other condition, two condition. I can go in a proper place, and my next queen also find a good position. In that case only, you return true, and you also make this as you have already made this one, because for you to call the recursive on the next, you have to place it also there. So what I'm doing first is check, can I be placed at ith row? Okay, first is check, can I be placed at ith row? And why is this not possible sometimes? Because the moment you call it for ith queen, some kth queen, all the queen before that would have been placed. So this might not be true for all. This will be true for the first queen, but this might not be true for all the rest of the queens. So first check is, can I be placed there in that ith row? So first check is that. Now if I can be placed here, now I'll try to place here, and then I'll try to call recursive for the next queen. And if the next queen also finds a place, which might not be true every time, if the next queen doesn't find a place or find a place, if this next queen finds a place, then just return true, because the next queen also has a found a place. Because the next queen also found a place, I have placed and then I return true. Otherwise, if the next queen can't find the place, I don't want to go there. I'll try for next I. I'll try for next I. Make that wherever you put me, just backtrack, remove me from there, and try for next I. This is trying for next I, and keep on doing for all of them. And we are sure that we'll be able to find. Hence, we'll keep on trying for all of them. By the time we reach n, we'll for sure get a position where rest of them can also be placed. So first, if you still haven't understood, let's try to compute the time complexity. If you haven't understood the solution, we'll come back. But let's try to compute the time complexity. Can you think about time complexity a little bit?
N cross n.
N cross n. Others, what can you think?
No, it is more than n cross n.
More than n cross n.
Yes. Because we are doing that loop again and again, because
yes.
See, if one is not matched, again we are trying to reassign all the queens again and again.
Yes.
Yeah, that is how it is working here.
Yes. So it is more than n cross n. What is happening is, for every n, we are trying to find the position of rest of n minus 1 elements for every n. So it will be it will be this thing we are doing this called recursively for all the queen, and each recursion is doing this loop. Okay, and I'm assuming the worst case, in every recursion which is getting called here, in every recursion we are trying for all the position. So every recursion we're trying to do for all the position, it will be we're trying each for every we're calling for each queen. So we are calling for each column. We'll go for each column one by one, and we try each row. So for this column, we try this row, this row, this row, this row, this row. And for what does that mean by row? It means finding the position for this. So I tried this and recursively try for the rest of the sub problem, and that rest of the sub problem is, I think it will be n cross n only. At the end, although it is we're just visiting each node only once. Are we visiting any node more than once? Any indexes more than once? So we are recursively calling for each queen. So we started with 0th queen, and we are calling recursively for the rest of the sub problem, this sub problem, and we call this sub problem for every So T of n will be equal to n into t of n minus 1. Is this correct?
Because here, if you consider for loop, we are iterating from initial row again and again. If you see in time
Yes.
equal to 0, again we are starting from 0 to n, 0 to n, 0 to n each time. We
Yes.
are not doing n t of n minus 1, I think. If you looks like.
So what is the time complexity with this? So this will be n factorial, not n. I mean n to n. It will be n factorial. Okay.
Yes. Okay.
Okay. Coming back to this solution, do you what part of the solution, which it took a lot of time to explain, what part of it you were not able to understand at all? What part of the code? I'll delete all this diagram first. I'll make the screen bigger. Now I'll discuss only with the code, not with the drawing.
See here, everything is looks okay, but the problem here is whenever it calls recursion, right? Solve it will that time. Each time it is starting from row again and again. I think that makes confusion. For starting, you said that's okay. Like for first iteration, it is okay. Whenever it calls recursion, again we have to come back from row 0. Then we need to do all those like, multiple.
So let's think the way whatever I discussed. What all we have to do for a recursive method. So one thing is returning. What shall it return? So it should return a true and false, something like that. It's saying we have written. Is that we want? So what we want is place n queen in an n by n board. That is what the requirement. Place n queen in an n by n board, and that is what just return. Just place it and done. We don't have to return a lot. Just place it done. So we just replacing if it can be placed or not. Also, I mean if it place and also return. We are just trying to return one boolean if it can be placed. So and using this we'll do something. So this is a return and we are reading. So if now that we call it, we assuming it is going to work. We assume that it is going to work, but where we don't know. We don't know which sub problem will be true. It is going to work, but which sub problem will be able true? That's what we have to find. Will this be true for I equal to 0 or I equal to something else? So we are calling this for all of them, and one of the sub problem will work. So out of one sub problem. So what do you mean by sub problem here is we are trying for all the rows. If you remember the diagram, we kept our first queen at the first in the first column. Now we have to try for rest of the 2D array and with the second queen. So this second queen, before we call this, we have to try for all the subproblem, which means the first queen goes at the first row, second row, third row, fourth row. These are the subproblems. First row, second row, third row. The queen is going at first row, the queen going at second row, the queen going at third row. All of them are the subproblems, and only one of them is correct. So we try for all the position, all the rows, and we call recursively for our next. We call recursively for our next queen in a changed board. This is the changed board. This board we are passing recursively. We are not just passing the sub problem. Do it for second queen. We are also passing one more thing here recursively. The updated board. And what is updated here is that your previous queen has been placed somewhere. With that, or not just that previous, but all the previous queen has been placed somewhere. With that placement, can you solve for the next queen? If you can solve, then we can solve completely. Otherwise, try to change your previous queen only and then try. So this is backtracking part here. Little bit confusing, not little bit, a lot of confusing for you here. But if I try to explain again for you, so we are trying this recursion. We are trying this recursion for all the possible value at that position. How it is different from normal? How it's different from normal recursion? In normal recursion, we know our sub problem, and we know that sub problem is going to work. in this case, we are not sure which sub problem will work. So we are trying for all the sub problems. And what are those all sub problems? All sub problem is myself getting at one of the row and then calling the sub problem that any one of them can work. So this part is for so this part is, and there can be another recursion type when I need the solution for all of them. So this is how this is different from a normal recursion is I will call for all of them, but only if I needed the answer of all of them. In that case, it would have been simpler for you that calculate for when this plays at zeroth row, calculate when this plays at 1th row, 1st row, 2nd row, 3rd row. So in that case, it would have been a normal recursion when your solution of the main problem depends on all the subproblem. What do you mean by subproblem? That main queen, the first queen going at 0th row, 2nd row, 3rd row, 4th row, and then calculate the value for all the possible situation, and then sum them up or find the maximum, something like that. That in that case, it would have been easy for you. Just call this recursion. I'm trying to keep a very simple recursion. Then we come to the tough recursion of this recursion. So solve for I equal to like pass it I, and then something like that. So solve for I plus 1, and then simply solve for all of them, and then depending upon the output of this, just take a decision at the end. Then this recursion would have been very simple for you to understand. I want to calculate for I equal to 0. First column, and that first column depends on the answer of all the other columns. So I call recursively for all the other columns with this. Not all the other columns, but next column only. But my value changing for all the subproblems. So that would have been really easy. But in this case, all recursive call might not be a solution. Hence, we have to check which recursive call is a solution. So and this is a recursive call with a little bit different. We're not writing it here because we are passing this board. You see, we are passing this board only. So this recursive, which is getting called for sub problem. So how it is changing. So this recursive method, which we are calling, how it is a little bit different. In this case, we're not passing the next subproblem value, which is not simply we're changing the board only, and then passing the same value for all the recursive call. For all the recursive call, we're passing the same value, but we're just changing the input only, kind of. So if you take this recursive call factorial, we were passing this subproblem. This is going to change. But what is happening in this question a little bit different is we're passing something same here, but we're changing the original. I'm not able to write here. But this recursive call is changing the board. This board, which looks constant, this is getting changed, but this is same every time. This is not changing. If you see this recurs for I equal to 0 to n, what we're doing is we're calling it n recursion, and each recursion we're not changing this call. This is same every time. What has changed is this board. The main problem only has changed. That kind of recursion this is, and not all of them will contribute to the main solution. Only one of them is true, and hence just get that true, and then finally we return the main. We decide which one is correct by backtracking, and hence at the end we have solved for all the queens. अगर अभी भी समझ नहीं आया तो I'm moving forward. If you have any, so now we have seen the code a lot. We have seen each and every line. So at least you should be able to understand this code. If not, the complete ये code समझ में आ गया है. Do you understand this code? Not lot of lines here. First line is just return if I have solved for 8th queen. This is the first line. Okay, I'm trying to talk in terms of 8. Okay, the return true. Yes, I have done for if you have solved for 8th queen. Now coming here, I'm solving for column queen, which is I have called here. I'm solving for column queen. I'm trying for this column queen for each possible row. So I'm trying for each possible row. For each possible row, I'm placing it there and then checking. So first I'm checking, can I place it? Yes, I can place. So I'm placing it there and then recursively calling for the next queen. If that next queen can find a good place, nice. I'll be able to just return true and then place it, then done, just return true, that's it. So this part is, if I can place the next queen at some position, then return true then. Otherwise, I can't place my this column queen at this ith, then remove it there and then try it in the next I. This is the part of the code. This is a mix of iteration plus recursion, where iteration is happening first and then recursion is happening inside. Shall I move ahead? या और कुछ तो भी करना है इसमें डिस्कस? Yes, I've unmuted everyone. Do you want anything more with this, or shall I move ahead with DP? Okay. Still, who has like पूरा ऊपर से चला गया? शुभदीप, कुछ भी समझ नहीं आया इस बार भी?
ना वो वाला तो समझ में आया, वो बोर्ड पे प्लेस करने का। बोर्ड पे कैसे प्लेस हो रहा है वो तो समझ में आया, और इधर तो समझ में आया कि कब सेफ है कब अनसेफ है।
Okay, safe unsafe तो easy है. The important part is, again, the important part is we are doing for all the queens. एक एक करके हर क्वीन क्लिक कर रहे हैं, और जब वो क्वीन क्लिक कर रहे हैं तब तक मेरा उससे पहले के सारे क्वीन प्लेस हो चुके जो चेंज नहीं होंगे, वो तभी चेंज होंगे जब मेरा करंट क्वीन को कोई जगह नहीं मिलेगा. सो आई एम रिकर्सिवली कॉलिंग फॉर ईच क्वीन. मतलब 0th क्वीन को रख दिया मैंने, उसके बाद मैं नेक्स्ट क्वीन का जगह ढूंढ रहा हूँ. इफ आई फाइंड द नेक्स्ट क्वीन का जगह, then it's okay, then just return true. If I find the next queen के लिए correct position, if next queen can be placed somewhere in that column, it is good. Otherwise, remove it from the this backtrack. This is the part of backtrack. This is important line. This is backtrack. नहीं, यहाँ जो तुमने place किया था ith queen को, if you place it there, you will not be able to place your other queens. So although it is safe to place ith queen at this column queen at this place, at this row, although it is possible, and hence I placed also, but when I checked for next, I could not find. Hence I had to backtrack. This is the part of backtrack. There are 3-4 lines, important lines. One is it safe to place the current queen at this position I? Yes, if it is safe, then only place. Otherwise, if not safe, try for next. This is, if you don't find safe, try for next I. If you find still is not sure, if you find, doesn't mean you can place it. You try to place it there and then try to file the solution for the rest of the board. If you find a solution, good, go ahead, done. Otherwise, if you don't find a position for the next queen, you have to remove it and try for the next. So there are two decisions where we are incrementing I. We are changing I. One is I can't only place the next queen at that I, then try for next I. Okay, there are two conditions I'm changing I. One is I can't only place my current queen at the ith row, hence I'll go for the next I. Otherwise, I'll do one more check. Is I can place I, but if I place that I, if that place that queen at that I, I'll have to. I won't be able to place my next queen at any place. Hence, I'll have to remove that queen and try for next I. So there are two conditions to try for next I. This is for that queen, try at I position. So this two things important: column and I. Column is I'm trying columnth queen, 0th queen, first queen, second queen, third queen, and I is I'm trying each row. Okay. Nice, and still you try to write the code without seeing this and try to implement. If you remember things, you'll be able to write. This is not a very lengthy code. Yeah, it is tricky, but code wise it is very small. You will be able to write, and once you write, you'll be able to get. Okay.
मतलब time complexity row plus column होगा या anything factorial कैसे हो रहा है वो समझ factorial क्यों हो रहा है समझ में नहीं आया.
Let's again, as I wrote, कि हम लोग what we are doing is we are trying to solve for n queen. Now this first queen,
8 cross 8.
Yes, let's talk 8. So so we are trying for 8 possible location for our 8th queen. Sorry, first queen. First queen we have 0th row, first row, second row, third row. So we are doing this loop. This loop runs 0 to 8. So 8 time. Now with this 8 time, when we have this 8 time, what we are left with is 7 cross 7 sub array. We are left with 7 cross 7 sub array. So this solution, this part, where is this? This part is for 7 cross 7 array. Not necessarily very adjacent to each other. It's not necessary that all those 7x7 array will be adjacent to each other. Only what will happen is one of the row and column will disappear. One of the row and column will disappear, which you cannot use. But if you delete, even if you delete that, let me draw something for you. So suppose I placed my first queen here. Now I can't use this row and I can't use this column. So what I'm left with is from 4 to 4, I am left with 3 by 3, or from 5 by 5, I'm left with only 4 by 4. So this for the first one, I have to try for all of them. For the first one, I have to try for all of them and call this recursively on the sub 2D array, which might not be very close to each other. So let me now suppose what I was trying for this row. In this case, my sub array won't be very simple. It will be something like all these row, this row, this row, this row, and this row. So this is also a sub array of size 4 by 4. It's not just close to each other. It's just like, okay, these 3 row, these 3, and this 3. So my point is, I'm trying for all the position of this, and for all this position, I'm left with a sub array of size n-1. If this was size n, I'm left with a sub array of n-1. Might not be adjacent to each other. There might be a gap, but I'll still be having a sub array of n-1. Hence, I have to solve for that sub array. So we are doing this for n times. We're doing for n times for all the sub array of n-1. So the time complexity was T of n is equal to n into T n-1. Time complexity for n is equal to, I have to try for all that into T of n-1. So this T of n-1 will be equal to n-1 into T of n-2. And if you just do this n-2, if you just repeat this till 1, it will become n into n-1 into 1, which is n factorial. ठीक है? नहीं?
हाँ ठीक है.
Okay. Nitesh, you there?
Yes.
Okay, whatever battery is remaining, why don't you join with the laptop? What has happened to your laptop?
I could not install Zoom in the laptop.
Okay. So let's come back to our dynamic program which we wanted to do today. But it was very important to understand recursion. Although we did a little bit of backtracking, but recursion was the most important thing. There can be so complex recursion as well. This is a complex recursive method. This is one of the most complex recursion method you will come across, where you're calling your recursive method inside a loop, and depending upon the and this recursive method is not called straightforward. We don't know. It doesn't look very simple recursive method. But coming back, yes. So coming back to our recursion, this is a recursive method where I try to give one more example of a recursive method. Done. Backtracking also we did a little bit. I have talked about this thing called tailed recursion. What is that tailed recursion is? Where your recursive is the last part in the code. The last line in the code, if that is a recursive call, then it is a tailed recursion. Okay, just most of the recursion will look like this only. Very last part of the code will be a recursion. This is called tailed recursion. Nothing special. Now coming to our DP. Now coming to our more.
The recursion is the first line.
That is not a tailed recursion. That's it.
What is the recursion is?
Yes.
Okay, we don't have a name for that.
No, there is no special name. That's you can call head recursion. You can call it head recursion, but it's not a very popular thing. Okay. Now this we have example of Fibonacci, this Fibonacci series which we have solved a lot of times. So my point here is whenever we solve for DP, you have to come up with the recursive solution. If you can find the recursion, you will be able to find the dynamic programming easily. So we all know this Fibonacci, the simple recursive method of this Fibonacci series, which is find the Fibonacci of n that will depend on the n-1 and n-2 called recursively. So if you see this, there are multiple, the complexity of this is very high, and hence we want to do something better. That making of this better is what is DP, like dynamic programming. How can we improve our unnecessary recursive calls and return a solution which is much better than our recursion. So first of all we have identified our recursion. So the DP solution will be where I've written this. So one thing here is this main solution is calling the sub problem, which is okay. But if we go deeper into this, our recursive call, we'll find that something which is called getting multiple times. Although we have calculated with this getting multiple times, and that term there, that is for we have overlapping sub problems. Okay, it's not that we call it on the left subtree and right subtree, and that we call it in its own left subtree and right subtree. But what's happening is it is getting overlapped. We called for 5, that 5 called for 4 and 3. This 4 will also call for 3. So this 3 which was called by 5 and which was called by 3 also, this is getting called multiple times, and hence it would end up being a exponential time complexity, and we would like to improve on that. So this is called if any problem, how to identify DP now. If you find a recursion along with the overlapping recursion. So this overlapping is important. If there is an overlapping recursion, then we should go for a DP. So first thing is find recursion, and second thing is overlapping recursion. Then only your DP is required. Otherwise, your DP not required. If you do not have overlapping sub problems, if you do not have overlapping recursive getting called, then you don't need dynamic problem over there. So how to now solve this? This is the recursion method, but which was taking a lot of time. How to solve this is I have talked about this earlier also. So when we know that we will be calling our recursion method overlapping problems multiple times, why don't we solve it for the first time we got it? For the first time we find the recursion, just save it somewhere so that next time we don't end up solving again. So this is what it's doing. It's like it initializes this array with lookup array for each value I, and started with nil. Okay, right now none of them has been calculated. I think I discussed this somewhere before, which was, where did I discuss this kind of question? Solve it for that height balanced or something like that. That is height balanced or not? Yes. So for our, if you remember, we tried to solve this for height balanced. So what we were trying to do was, we were trying to, it might not be a DP there, but it was similar on similar lines, that if I'm calculating the height of a node, I'll also store the height there only, so that if I end up calculating height once again, I won't calculate again. This is on that similar line. If I call recursively for a node, or if I call recursively for a position, or I call recursively for an input value I, and if I have already calculated for the I won't be calculating again. I'll just store it somewhere. So that's what I've done here. I initialize with an array, lookup array, and I started with an initialize with nil. Everything is a nil. Okay, Nitesh, you can leave now. This video will be there. Okay, bye. Yeah. So this recurs, we have all. Yeah. So we have this initialize with nil, and now I'm trying to calculate this Fibonacci of n, and I'm calling it recursively again. I'm still calling it recursively. There are 2 recursions. Okay, and I'm before I'm returning this value, I could have earlier what I was doing was I was storing in a variable, something like this, some variable I, something like I was showing you here, and I was returning I, something like this we were doing. Okay, this solution was something like this. I was returning into we could have stored it into I equal to this and return I. This is what we were doing. We're not storing anywhere, but with the DP, what I'm doing is before I'm returning, I'm storing that value into this array. So calculate recursively for sure. This is recursion, so calculate recursively. But whatever the value comes, store it somewhere, so that now this storage will happen for even recursive method as well. So the next time you call that again recursively, my this lookup array would have been already containing the actual value. Hence, I won't call this recursive will not call deeper. This will go deeper only for the first time. Fibonacci of 4, or like suppose we start with 10, and suppose 10 was we started with Fibonacci of 10. 10 called 8 and 9. 9 called 8 and 7. 7 called 8 called 8 and 7. So suppose this Fibonacci of 5, that will be called multiple times. But only first calculation will take time. Only first calculation will take some time. But after that, it won't take time at all, because that would have already been calculated and stored in our lookup value. That is what we're doing here. So if you get this solution, what we're doing is we are starting from, we're trying to calculate topmost value lookup of, we're trying to find the topmost value, which is n, which depends on the smaller value n minus 1 and n minus 2. And we're calculating that order only, and we're storing into our lookup array. And at the end, we'll just return our lookup of n. This is what we're trying to find. This, if you see, this is called top-down approach. Our recursion is going from top to down, and we are storing value also from top to down every time, so that we don't have to calculate again. This is called top-down approach. This is one of the way to solve a recursion by storing value, and hence it's called DP. This is one of the DP solution. DP can be two type. DP solution can be two type. One is top-down and one is bottom-up. Same solution can be solved a little bit different. Where what we do is we start from a recursion. We start an iteration from 0th value, and then keep on calculating for every value from 0, 0, and then 1, then 2, and then 3, and then 4, and then we keep on going from bottom to up till f of n. And the moment we have calculated our f of n, we just return that. This is a bottom-up approach.
Here, Praveen, I have one question. How we are going to differentiate it is bottom-up and top-bottom something?
You will not. I won't be able to give you the direct answer here. We'll have to see this question, and then only we'll have to take a call by seeing the question. There is no special rule right now with me.
No, this one. Consider this one itself. You said both are returning Fibonacci series for the final value.
Yeah, it's not that only one solution will work. Both of them can work. You can write either of them.
Yeah. So then, how you said like it is a bottom up. Here we are not doing any recursion, but here we are initializing two values. We are summing up. That's it, and we are putting into the next value. Yes. How you are saying it is bottom up means I'm thinking. I got both the solution, but I'm not able to understand why it is bottom up and top bottom.
Yes. So first of all, we know that there was a recursion, and we know that there was a bad recursion. Okay, we got it. There was a bad recursion. So we want to change this and get a better solution. So we had another recursive only, but with a storage recursive. Okay, this is a recursion. This is also a recursion, but with a storage as well. We are storing value somewhere. We are calling it recursively, but with the storage. This is not a recursion. I'm not saying every recursion will be solved by a recursion only. Every bad recursion will be solved by a DP. That DP will look like either a recursion or not, or some other way. So both of them are DP. Both of them are dynamic problem, dynamic programming solution only. But this is a recursive kind of solution. This is an iteration solution. Now, what is this top-down and bottom approach? So top-down and bottom approach is we want to calculate the value of n. We want to calculate the value of some root node. We want to calculate the value at some input. So that input depends on its sub-problem. Sub-problem is input by 2 or input minus 1 or input by 3, something like that. So bottom up and top down is, in this, the bottom up, we want to reach at the nth position, which the actual question. The actual question is find the Fibonacci of n. So to calculate Fibonacci of n, we needed a solution for n minus 1 and n minus 2. So n minus 1 and n minus 2 required a solution for n minus 2 and n minus 3. So if I try to go from that way, top to down, like from n to n0, that is called top to down. We are trying to fetch the solution for this by calling recursively for its children n minus 1 and n minus 2. It will end up, it will stop here when n is less than or equal to 1, and it will just save it without calling recursively. It will just save the value, lookup of n equal to n, or that is lookup of 0 equal to 0 or lookup of 1 equal to 1. That is the point. We'll stop this recursion. Otherwise, we'll call recursively for the smaller values till we reach the smallest value. We start with a bigger value or a bigger problem, and then we reach the smallest value or the smallest sub-problem. In this case, we started with the smallest sub-problem, we 0 and 1. The problem is that finding Fibonacci of n requires you to find the Fibonacci of 0 and 1 also. If you don't know the Fibonacci of 0 and 1, you cannot find the Fibonacci of n. So we just started with 0 and 1. We knew the value. Then we tried to calculate for 2. Then because that was the immediate bigger problem, 2. How can we find for 2? The 2 for 2 I can find using 0 and 1. So then I tried to find for 3. So we're starting from the smallest sub problem and reaching to the bigger main problem. This is like bottom up. Start with the smallest sub problem, try to solve for 2, try to solve for 3, try to solve for 4, and then keep on going up till you find solve for the nth. And this was okay. I want to solve for n. I just want a solution from n minus 1 and n minus 2. I don't care about how do you get it. Just get me solution from these two, and then I'll use those two to find the solution of my n. So this is both the solutions might work everywhere, or only one can work somewhere not. But these are two. Most of the time, these are the only two ways to find the solution for your DP. So DP is what? Recursion with storage. In my terms, they're not written somewhere. What is DP? DP is a recursion, or not necessarily solution to a recursion, not necessarily a solution to a recursion using storage. Either you store whatever you're calculating from top to bottom, or you start from scratch. Okay, I want to calculate for suppose there's a problem. That problem of so most of the time your brute force approach will look like this only. I want to try for all of them one by one, and then I end up reaching a solution for that position. This kind of brute force will also look similar. To find for n, I have to find for 0, and I have to find for 1, I have to find for 3, 2, 3, 4, 5, and I have to try for everyone, and at the end I have to try for last thing. This is a little bit sometimes similar to our brute force also. Let's take one question, and then we'll try to get deeper into these two. So one more property it has like every time we also we'll try to identify if that problem can be reduced to 2 problems, and the optimum solution of both those sub problems, or not just 2, and the optimum solution of all the sub problems can be used to get the optimum of this. So for example, the shortest path problems. There are questions like find the shortest path between 2 nodes. To solve that, if we know if we can break into n sub problems, like suppose I try to draw. So there's a graph. If you know graph, so I want to find a shortest path from here to A to B, and there are multiple other paths. So what is the shortest path? For us to find the shortest path between A and B, what we can tell that there are multiple intermediate points in that path, and for that intermediate point, if I break that into two sub problem of from A to that intermediate point, and from that intermediate point to end point, if I have found the optimal solution for that sub part and that sub, then I have the optimal solution for the biggest question also. So this is also one property. If that property not getting satisfied, then you won't be able to apply your DP there. So let me delete this. So if you are able to solve your sub problem, and you know if I can solve my sub problem optimally, both the sub problem, then only I can solve my main problem. Then it's a DP problem. So finding a smallest path is the kind of DP where you store the value of the sub problem and use that. But finding the longest path is not a optimal structure property. It does not have this optimal substructure property. What does that mean? That if I take a smaller sub problem that is path from A to B, if I break into A to I and I to B, and longest path from A to I plus and the longest path from I to B, can that be used to find the longest path from A to B? No. Then in that case we cannot apply our DP. So this is another way to think: can we use DP or not? Let's talk a question again, and then we'll think about these properties. One property is overlapping sub problems, that your main problem should have overlapping sub problem. That's very important thing. If it doesn't have, we won't be using DP. And second is this second property is the optimal substructure property, that the substructure or the sub problem. If you know the optimal of that sub problem, then we can find us optimal of our main problem as well. So let's take a question now. A very simple question: that what is the total number of ways to get sum 6 from this array. This is array 135, and we have to calculate what is the number of ways to make 6. So 6 can be made like 5 plus 1, or 3 plus 3, or 1 plus 1 plus 1 plus 1, or 1 plus 3 plus 1 plus 1 plus 1 plus 3. There are multiple ways you can construct, you can make 6. So what is the total number of ways you have to find? Question समझ में आ गया सबको? You get the question?
Yes.
Yes. So try to think, and what you'll think is, I'll just try to write here whatever I've discussed, how to think of DP is. First is recursion. I've written somewhere. Think about the recursion. Think about storing the value. Yes. So first thing is, think about the recursion.
There
So
is only
here-
one way, right?
Yes.
So if I'm not sure if I understood the question correctly, the solution here is only one, right? So
No.
5 plus 1 is 6.
No. So total number of ways to get 6. There is multiple number of ways to build 6 out of these 135, and you can repeat the numbers. There are multiple ways to build 6 using 135. 1 plus 1 plus 1 plus 1 is equal to 6, and 1 plus 1 plus 1 plus 3 also equal to 6. So that is 2 ways. Third way is 1 plus 5. Third way. Then fourth way is 1 plus 1 plus 1, and then 1 plus 1 plus 1 plus 1 6 times. And I mean, all these ways you have to add up and tell what is the number of ways to find to build 6 with these numbers. So before recursion, just try to write the method. Number of ways. The moment you write the number of ways to build 6 using the input array, which is integer array A, this will return your int. First thing is this. If you write this, things will become a little bit clear. And second thing is recursion. So let's try to write. Okay, let's try to recursion. Let's call it recursively. And let's just call recursively for small array. Small array. What will that small array we have to think for smaller a? What will that small array would be? Will there be only one small array, or will there be more than one small array? Will there be smaller a1 and a2 and like this, or will there be only one? Okay.
ये A1 A2 क्या है?
A1 A2 क्या है? So what I'm saying is you have to think कि what is the recursion. So I'm saying recursion तो होना ही होना है for sure. So what that recursion is it, either I might call recursively for a smaller a, which might be a by 2 or like half of the a, or I might call it for one element remove, 2 element remove, something like that. So there are multiple sub a's. I don't know what the sub. I've written it very name. You have to think about this sub problem, but first think about the recursion.
The question है कि using 1 कितना way से 6 find कर सकते हैं, correct?
No, that's not the question.
So 1 plus 5 equal to 6.
Yes.
Okay.
Question is, what is the number of ways to generate 6 from this array? So this array has 3 elements. You can sum up these values, either of them, and you can repeat also. So one way is 1 plus 1 plus 1 plus 1 plus 1.
Okay, got it.
Other is 1 plus 1 plus 1 plus 3. Other is 1 plus 5. Anything else?
Three plus three.
What?
Three plus 3.
Yes, 3 plus 3. Yes. So the number of ways is, right now we can see 4. There might be more, but that's what you have to calculate. What is the number of ways to generate 6? Question 7 में आ गया है, तो then start thinking on the lines I told. First, the signature of the method, and this is the signature of the int number of ways for the array A. Now second part is recursion. Think about the recursion. क्या हुआ? No one.
कंडीशन पता चली, कंडीशन ब्रेकिंग कंडीशन रहेगी कि अगर सम इक्वल्स टू 6 आ रहा है तो काउंट हमारा बढ़ जाएगा और वहां से निकल जाएंगे। नहीं,
Okay.
ब्रेकिंग कंडीशन नहीं होगी, वो तो काउंट बढ़ेगा सिर्फ, हमको नंबर ऑफ वेज चाहिए तो।
So we'll come to automatic condition. We'll talk about the base condition, but before base condition. But first, talk about the recursion. So number of ways to calculate this. So number of ways to calculate for this big array A will depend on what if I so this using A for some int sum. मैं generally लिख रहा हूँ. So this first we are now number of ways to calculate this depends on sum minus let's keep it outside that we had some for simpler recursion for example. So we had an array with numbers. Now number of ways to calculate for 6 will be equal to number of ways to calculate for 5 plus number of ways to calculate for 3 plus number of ways to calculate for 1. So what I'm doing here is this main method, which is trying to calculate the number of ways to calculate 6, depends on number of ways to calculate 5 and number of ways to calculate 3 and number of ways to calculate 1. If I get so and then why? Because if I calculate this for 5 and if I calculate this for 3 and if I calculate the same thing for our 1, we just 1. If I have these things calculated, then I can just sum these up because this number of ways to find 5 and we can add 1 and get this. So अगर ये दो तरीके से, if you have 2 ways to find 5, then to find 6 is just 2 way only, 1 plus the number of ways. Okay, same number of ways, just add 1. That is what this becomes. And similarly for 3, similarly for 1. ये समझ में आया? What we are doing here? I'm just replacing again. So number of ways to find sum depends on these 3. If we have calculated these 3, then we can just add these up and get the sum and sum of these 3. So in this case, I will not one thing I'm using that 1 remaining part of only for 1 sum minus 1. I'm using 3. Now remaining part is sum minus 3 and I'm using 5 and remaining part is sum minus 5. So if I calculate for these 3, these all of them, we can find the solution. Is it tough, this recursion? We haven't written the base condition yet. But is this recursion tough to understand?
No.
Okay. Now let's try to write a base condition. Can someone tell me the base condition? So this is return. Okay. First of all, we have to write return. Otherwise, return this. What else?
Here,
so
here we need to do some count
Some?
in the sense. We need to pass +1 or somewhere, I think looks like.
No, so base condition would be, so what is the base condition? Something we do not have to calculate, something we know from our knowledge. Like, okay, इसका इतना ही होगा ही होगा. So
sum less than equal to 0.
Yes. So if sum is less than equal to 0,
then return 0.
Then return 0, 1 or 0, 1.
1.
Okay, and that is do not include any number. Okay, so this is returning 1. So if we have this thing, this is one return with the base condition and one return with the recursion. Two returns should be good enough. Then we don't need any other base condition or any other So with this it will work. Sanaya?
Yes.
So this is a recursive solution, and the time complexity of this would be?
This one will be n. Sorry, n sum.
No.
n factorial.
Not in factorial. Looks like factorial.
First
It's
time
not factorial. This is exponential.
Okay. Looks like.
This is 3 to the power n. This will be 3 to the power n. Okay.
Because there are 3 numbers, इसलिए 3 है और उसके
Yes.
लिए n नंबर टाइम चलेगा. n क्या है इसमें?
N is this sum.
Number of element. Okay.
Sums. No. N is sum. 3 is the number of element, and n is sum. So I'm assuming every time I'm going one level deep, every time I'm going one level deep, we're just decreasing sum by 1. That's the worst case. एक ही घट रहा था. Although we have some decreasing by 3, some decreasing by 5. So this part of the sub problem will not go n times. Will go n times. The left this will go n times. This will go only n by 5 times. Understand what is happening here? I'm decreasing 1 by 1. So this will be n level deep, and this will be only n by 5 level deep. क्योंकि हम हर बार n कम कर रहे हैं, n 5 कम कर रहे हैं. So, but we don't care about those 1 and 5. What we care is at every level we are calling recursively, and we are decreasing our sum. And what is that decrease? This is decreased by 1, 1, 1, or something, some constant. So which let's take averages. कि हम we are decreasing sum by 2 to 2. So it will be for every level we have just 3, and then we have 3 plus 3 plus 3. Then we have again 3 plus 3 plus 3, and this is happening n by 2 times, or average. I'm taking average n by 2 times. Worst case n times, and best case only n by 5 times. Okay. So this is this thing we are doing. 3 to the power n. This will be 3 to the power n by 2 or whatever. But at the end it will be 3 to the power something, and that something will be some by 2 or some by 3 or some by something. So it will be it won't be exactly 3 to the power sum, because only one will be that much deeper. Only one of the recursion will be some level deeper, because we are depending -1, -1, -1. The other won't be that deeper. It will be only the minimum dip. The minimum depth will be n by 5, sum by 5, because we're decreasing 5, 5, 5. So after like suppose we're doing for sum equal to 55, then after 11 deep recursion it will be over, because we'll reach 55 minus 5, 50 minus 5, 45 minus 5. So after 11 recursion we'll reach our 0 and we'll return the best condition. But on the left side we'll do 54, 53, 57. We'll have to do it 55 times. And at every level we are again having 3 children. So this children will again go for 50, 54. This will go for something less than 54. But worst case would be we'll do it for 3 to the power n times. This is a worst case. Exponential, at least exponential time. Okay? Okay?
Yes.
Yeah. So now we have tried to we have found our recursion, and we have written our sub problem. Next part comes the DP. How can we and what can we store so that we don't recalculate that? By the way, this is top down. This is top down. We are coming from the sum and we are decreasing it, and with small problems, and we are calling it again deeper into smaller sub problems. So this is top down approach. We will try to do a bottom up as well. So, but before that, how will you solve it top down only?
So top down means we need to start from the maximum one.
So forget about the top down right now. Just think about what instead of what is the overlapping sub problem here? What part is getting overlapped? So there's a part which is getting overlapped. This 6 will call on 5, 3 and 1. So this 5 will again call on 4, 2 and 0. So this 4, 2 and 0, this will again call 3, something minus 1 and then 0 will return. So this 3 will get called twice for this main also and this here also. So we do have a overlapping subproblem. So where can I store the value of these overlapping subproblems? And what are those overlapping subproblems? So overlapping subproblem is all the possible values. All the possible value of this. So we don't know exactly what all will be called. So we'll just try to initialize a storage with all the possible vacancy. I mean, we might not need to calculate for, suppose we'll not need to suppose we started with something very big number 60 and we had this, suppose this is all the number like more than this. So to calculate for 60 we might have to calculate for 59, 58 and 57, 55 and we might not have to calculate for 57 at all, but still we don't know what all we have to calculate. We just initialize an array from 0 to 60 so that we have, even if we have to calculate recursively for any of them, we have a storage. So now my point is what will that storage be here? What will that storage be? We'll have a storage A which will be an array of size sum. So what this will do, sum is the input. So what this will initialize an array from 0 to 6 and whenever we calculate for 6, we calculate for 4, 5, 1, whatever, and that will call internally, which just to keep on storing for all the values which is going to get called. We might not be calling some value that will remain empty. That's not a problem, but we'll store every value. So can someone change this to a DP now? If you've understood. If you haven't understood, tell me. I'll explain again. If you've understood, try to write the DP solution of this. Try to initialize the Try to initialize the yes.
Yeah, here what we can do, we can initialize DP into maximum size like sum.
Okay, so let me call it output array. Output is equal to an array
of size sum.
Okay, int of size sum. This we started with, and all of them are initially not calculated. So let's try. Let's try to. This is some array of size sum, and let's try to initialize all of them by something which is for sure indicator that it has not been calculated. For I equal to 0 to. So this is the way we write base condition in our recursion. We have to write a base, not condition, but we have to initialize our base array. We have to initialize our base input. So this is what the counterpart of recursion. In recursion, we write a if n equal to 0, then return this. In this DP, we'll try to initialize our base condition, base case. So for I equal to 0 to I less than n,
less than equal to n, equal to sum. Here we need to
and simply just
return number of ways sum minus 1.
Output of I is equal to -1. This is not been calculated, and then now write the base condition. This is not a base condition. This is the base condition. Output of 0, we know. What will that be? Output of 0, 1. Okay. Now with these two, an initialized but not yet calculated array, an initialized but not yet calculated output array, or I'm calling it array, any storage, initialized but not yet calculated storage, and one of that is also calculated, which is base. Using these two, we can call our recursive method. Okay, what we'll do? Yes, Vasant.
Here, are we using recursive or just for loop? We can do it in two ways.
Anything
let's go with for loop. Like I will start from for I equal to 1 less than equal to
less than equal to
sum I plus plus.
Okay, now
here one more thing I need, because here output of 1 and I'll define we can assign some more values to output. Why I'm saying, because anyhow we know, we calculated how many ways we can define 6
So what
using
will
3 and 5. Like
yeah?
what
So
I will
what
do
will
here,
output of 1 be?
1 again.
1. Okay.
Output
So
of
actually, you don't need to even you can do it without this. But let's initialize. Can someone tell me what this means, by the way? What is the meaning of output of I equal to X? What is the meaning of this line? Can someone tell me like what is the meaning of this line?
We are trying to store the result into one.
Yes, we are doing that. But in other words, we can say output of
Number
I
of-
equal to number of ways to generate I sum instead of sum, number of ways to generate I equal to X. This is what it means. Number of ways to generate I from this same array of 1 through 5. What is the number of ways to generate I? Okay, that is what it means. Okay, go ahead. So we have this loop.
yeah.
What
Then
I?
I equals to, here we can start from 2 directly. I equal to 2 instead of, we know 0 and 1. So
Okay, from 2 to 1.
then output of I minus 1 plus output of I
This
minus
is equal
2.
to, no? It's equal
Yeah,
to
equals
saying.
to. Yes, equals to.
Okay.
Sum
I
minus
minus
I minus 1 and I minus 2.
I minus 1 y2.
Okay, I minus 1 is an, if I go for I minus 2, yeah, it is I minus 1. That's enough, and we need to do some plus conditioners.
So output of I depends on 3 things. Output of I minus 1, I minus 3 and I minus 5. This is what recursion was saying. I minus 5.
Yeah, here it will go to negative condition if you see. Then
Yes, so you think about the generic first and then come to solve the
okay.
edge cases. So
Okay.
output of Y will depend on these 3.
Yes.
And then once we have calculated, we have to return as well. Why have to return? So every time this you have to do in almost all the recursion. Return and store. So first store and then return. This is very much necessary. First store and then return. And then let's not talk about the edge cases. So we have initialized some of the base cases. Now let's talk about the edge cases also. If by the way, this is not output, this is number of ways. Mistake.
वही तो तब से बोल रहा हूँ.
Wait. Think. Sorry.
So this is, we are using for loop. So
No.
that is correct.
This is
Recursion
top. No. This is not recursion. This is top down. Bottom up. We already have 0 and 1. Using 0, 1, can we calculate our 3? And using 0, 1, 3, 0, 1, 2, can we calculate 0, 1? So we're going from bottom most, and then we generating our something here, and then we calculate for output of 3. Then we calculate our output of 4. So every time we just incrementing our I and trying to calculate that depending upon old calculated value. This was already pre-populated, and hence we are calculating. This is not, we're not writing recursion at all. So Pradeep, you might be reading why you are not writing recursion. That's another solution. This is another solution. This is a solution in which we are trying to use the smaller values which has already been calculated somewhere to calculate the next value. So this is going from 2 to some, and we trying to calculate for 2, then 3, then 4, and then 5, and then 6. By the time I reach our n, I would have calculated from 0 to n minus 1, and using that 0 to n minus 1 or sum, not n, you can use those smaller values to calculate further, and then at the end just return that. So yes, so this code looks good to me. Just we have to handle a few more cases. If sum is less than 0, and then return 1. Okay, no, I don't want to store anywhere, just return. Okay, we have handled edge case as well as everything. We have handled this thing. Simple to understand. This is a simple dynamic DP compared to the other solution which Subodhi you might have been thinking. Let me try to write that as well. The other recursive call. So let me just copy this.
But here, Praveen, my question is, we have to predefine output of 0, 1, 2, 3, 4, and 5. Up.
Here you have to define till 5.
If you consider, yeah, till 5. Otherwise, yeah, then for loop it won't work, right? So at least 5 output of 5 we need to define.
Let me think.
Yeah.
Do we have to? If I start from here, if this is going out of index. Yes, if it say index not found, like wrong index, in that case we'll just define for all the basic yes, so that we don't have to.
Then we can start from 5 directly.
Yes, or 6 directly. We have, so that we don't end up making 5 minus 5. 5 is okay, so that we don't end up reaching negative index.
Yes.
Now let me try to write the other solution, the top-down approach, which some few people might be thinking is this solution only. So in this solution, what we're doing was we were storing the values in an order. We are storing for 5 and then 6 and then 7, and then like we growing one by one in an order. We calculating all the value in an order, small and like for 5 and then I plus 1, I plus 2, I plus. The other solution, which is top down, in this also will store. This also will have our output equal to integer of size sum. In this also we have this storage, but this time we're not sure in which order we calculate. We're just calculating and we're storing whenever we are able to find. So if sum is less than equal to 0, then we might have to initialize again something. I'll come to that place. So before I return, in this case, won't just return. I'll first store. If output of sum has not been calculated yet, is not equal to -1. So when I initialize this, I initialize with everything into -1. I did this. This initialization was not needed for the above solution. Actually, this initialization of for I equal to 0 to sum, output of I equal to -, this is not needed for this iterative solution. This is needed for this recursive solution. Okay, so we're writing this. Sorry, yeah. So for I equal to 0 to I less than sum, I plus plus, I have initialized with this, so that this is a marker that I have not been calculated yet. We had this. Now I write my recursion for number of ways to find sum. I'll first remove this paste and I'll do it later. If output of sum is not equal to -1, this means it has been calculated. This means it has been calculated. Let's talk about this not calculated yet. In that case, what we'll do is output of sum is equal to recursive call to all three. This is recursion now. This is a recursive call, and then return. So I have calculated, I have stored for sum, and I will return also. Return output of sum. I haven't written the base condition yet. I've just written a generic solution for a normal I or for normal sum. What it does is first it checks whether I have been calculated or not. If I have been calculated, if I have not been calculated, then calculate. Otherwise, just return whatever is stored. In both the cases, I'm returning is output of sum only. Either it would have been calculated earlier. It was not -1. Then just return the same thing. Otherwise, first calculate it using this recursive call, and then return the same thing. So what will this do? If I calculate starting with 6 will call for 1, 3, and 5. That 1, 3, and 5 will internally call for 0 and 1 and 0 and 1 and 3 and once again. Now the second call to this number of ways. Let me write something. This number of ways was called for 6, which was called internally for 1. This was called for 3, and this was called for 5. This again will call again for 3 once again. This part will call for 3 again. this, and this will call for once again. Now these problems, the first time it was doing, it will call, but the moment it has been calculated for the first time here, it would have been calculated here. It won't go deeper and will just return output there. So it will be order of 1 that at that point of time. Hence total uh, complexity will not be depending upon the number of recursion it is going, because it will stop. It won't be that recursion won't go deeper. So yes, this is another solution. Apart from this iterative solution, this is also top-down recursive solution for the same DP. We're just storing everything to our output. This output was the thing which has helped. This is the place where it is helping. If it is not calculated, then calculate, otherwise just return. So this and calculate and store, calculate and store. So every DP will have this, calculate and store, so that it can be used. So this is calculate and store, and then return whatever is stored or whatever is calculated. Both the approach is simple because the question is simple. Okay?
Yeah. The first for loop also takes a number of times and the time complexity. The second one also takes same thing.
Yeah.
Right? Yeah.
Yes. So both the algorithm gives order of n complexity.
Praveen, one thing I am trying to understand. ये दो सॉल्यूशन किया करेक्ट, तो एक में ये दो सॉल्यूशन अभी किया करेक्ट. वन इज आउटपुट ऑफ i - 1, वन इज नंबर ऑफ वेज. ठीक है, तो अभी एक में रिकर्सन यूज हो रहा है, एक में रिकर्सन नहीं हो रहा है.
यस
नहीं हो करेक्ट.
यस,
अभी डीपी मतलब ये है क्या कि मतलब ऑलवेज रिकर्सन होगा ही, ऐसा कुछ है? हार्ड एंड फास्ट रूल.
DP, the rule is it would be a recursive solution. Yes, it would be a recursion question, and not just recursion, but a overlapping recursion. Not just recursion. For sure, it will be recursion with a special recursion of overlapping. That also has to be there. Then only DP. So your question is, क्या DP में हमेशा recursion होगा? Yes, DP में हमेशा recursion होगा, and it would be a simpler recursion like binary search tree or binary search. It would be a bad recursion of overlapping problems. Okay.
तो ये प्रीवियस जो सॉल्यूशन है उसको हम लोग डीपी नहीं बोलेंगे क्या?
किसको?
आउटपुट ऑफ i जो है.
No. So both of them are dynamic problem. Question is the dynamic problem solution. Both of them are dynamic problem solution only. I'm not saying कि DP से ही recursion से ही solve करना है.
Okay.
The DP not necessarily it will be solved using a recursive way only. It can be solved either of them. What DP means is you are not calculating something already calculated. This is dynamically. I don't know how exactly is the word related dynamic problem. The thought process here is the recursion had a bad thing that I had to recalculate everything. So I'll be storing the values dynamically somewhere, either top down or bottom approach. I'll be storing the values. The first time I'll do recursion. The first time I calculate some value, I won't calculate that again. That's DP about. It's not about should we call it recursively or iteratively. Both of them are DP. Both of them. Okay. Okay.
Yeah, Praveen, I have one question. The thing is, can you tell me using 3 how many ways we can form 6? Like 3 plus 3 one way, another one is 1 plus 1 plus 1 plus 3. That is one way. Will it be like another way is 1 plus 1 plus 3 plus 1? Will we consider it as another way or what?
No, just placement is not a factor anymore. We are not worried about placement.
Just how many times that is present, like that's it.
Yes,
no placement matters. Okay.
Yes.
Okay. Can you scroll down a little bit? Just I'm seeing one. Yeah. Okay. Yeah.
ठीक है?
Yes.
Shall I move ahead? Next. Athar, you're not speaking. समझ में आ रहा है?
थोड़ा ऊपर से जा रहा है मुझे, but I will go through the video again. पूरे तरीके से ध्यान नहीं किया. I will go through again. और मुझे अगर कुछ
अब ऑफर आ गया तो ध्यान देना छोड़ दिया ना.
मंडे दे रहा हूँ मैं ऑफर आने के बाद भी. कल भी मेरा ऑन साइट है.
Okay. Okay, so see, the start of the class was confusing, so it ended up this become confusing.
Backtracking में थोड़ा link टूट गया मेरा.
Yes, I understand. So actually मेरा भी थोड़ा सा सोचने में टाइम लग गया था, तो it was yes. So understand that it took me some time to understand the solution only, because it was a random that I picked up. So anyways, if you forget about backtracking, just come back to recursion, and then how are we changing the recursion to DP? That's we are trying to understand. Yes.
Can I end this call? Actually, here it is too late for me.
What?
Can you end this call now, or it is 3:30 afternoon here? I have another meeting.
Okay, it's 1 o'clock and
Yeah.
ठीक है. If you say we can end here. We'll try to do a longer class on Sunday as it's needed by people, and we want to finish things fast. So we'll try to do bigger, longer class, and that bigger, long duration would be around 4 hours, not more than that even. So, and that timing would be IST.
हेलो.
So what is the
Hello.
time?
हाँ, शायद connection
somewhere around 11:30 to 12 IST.
Morning or evening?
AM.
11:30 AM or 12 noon.
Okay.
Vasant, is it okay for you?
It is morning. What is the time? It is midnight, I think. Midnight, 1 o'clock, I think. 1 to 3 some.
So
अरे
right now
मेहनत
it's
कर ले, कुछ नहीं होता. Start अभी 1-2 दिन.
Night out.
Night out मार दे, कोई नहीं. मैं मेरे तरफ से बियर तुझे.
Okay.
Dude, I deserve one beer.
Yeah, definitely.
Okay.
You are getting a pura cart of beer.
What's feeling of this?
Okay.
Yeah.
So either 11:30 or 12, because that class might extend a little bit. So at max we'll start at 12. Okay.
ठीक है.
Sunday or Saturday?
Sunday, not Saturday. Saturday I have office.
Okay.
Okay. No problem.
Okay.
Yeah.
Bye.
Okay,
Bye.
Bye.